The shear force and bending moment diagrams are very useful tools that help us to analyze a beam under loading. In this video, let's see what are shear force and bending moment, how do we find out their values, what is the sign convention usually adopted, and how to draw shear force diagram and bending moment diagrams. When a beam is loaded, internal forces will develop in it to maintain the equilibrium. Let's consider a section at this location. The internal forces developed will have two components. First one, we have the vertical forces oriented along the cross section or perpendicular to the axis of the beam. Next, we have normal forces oriented along the axis of the beam perpendicular to the cross section. The resultant of these vertical internal forces can be termed as shear forces. Coming to the normal forces, if a beam is sagging like this, the top part will get shortened, so the normal forces will be compressive. Bottom fibers of the beam will be stretched, and so the normal forces will be tensile in nature here. Each of these normal compressive forces will have a corresponding tensile force which is equal in magnitude and opposite in direction. So there won't be any net normal force, but these forces do produce a moment. So we can represent the internal forces acting on a beam cross section using two resultants. One is the shear force, which is the resultant of the vertical internal forces, and second is the bending moment, which is the resultant of the normal internal forces. The shear force and bending moment diagrams represents the values of these internal forces at each location along the beam. The resultant shear forces and bending moments acting on the beam depend on various factors such as loads acting on the beam and the support conditions of it.
The beams can be loaded in a number of ways.
That can be concentrated load, distributed load. In this, distributed loads can be of uniform type or varying type, and concentrated moment. Beams can be supported in a number of ways like pinned support, roller support, and fully fixed support. Each of these supports restrains the beam in different ways. Pinned support prevents horizontal and vertical displacement but permits rotation. We know if any degree of freedom is restricted at a support, there will be a corresponding reaction force or reaction moment at that location. In the case of pinned support, since horizontal and vertical displacements are prevented, there will be reactive forces in horizontal and vertical directions. Since rotation is permitted, there won't be any reaction moment. In the case of roller support, vertical displacement is restrained, but horizontal displacement and rotations are allowed. Thus, there will be reaction forces in the vertical direction only. Whereas the fully fixed support restricts all these movements, which result in reaction forces in horizontal and vertical directions as well as reaction moment at that support. Now let's see the sign convention usually used for the shear force and bending moment calculation. This shows the positive sign convention. If the beam is on the left of the section, the shear force pointing downward will be positive, and if the beam is on the right of the section, the shear force pointing upward will be positive. Bending moment will be positive when it leads to the lower portion of the beam to tension, that is sagging. If we speak in terms of external loads, we can say the load pointing upward at the left of the section will produce a positive shear. Similarly, the downward force at the right of the section produces a positive shear. The external force pointing downward at the left of the section and pointing upward at the right of the section will give rise to a negative shear. In the case of bending moment, the sagging is considered as positive. So the loads which leads to a clockwise moment at the left of the section and anti-clockwise moment at the right of the section produces a positive bending moment. Similarly, the load which leads to an anti-clockwise moment at the left of the section and clockwise moment at the right of the section both produces a negative
bending moment.
Now let's see how to determine the shear force and bending moments within a beam. There are three main steps we need to follow.
First one is to draw the free body diagram. Second is to calculate the unknown reaction forces and reaction moments at the supports. Next is to calculate the values of shear forces and bending moments at preferred locations along the length of the beam. I will explain these with the help of an example.
This is our beam. It has pin support on one end and other side we have roller support. Two concentrated loads are acting on the beam and 15 kilonewton is at a distance of 2 meter from support A and 10 kilonewton is at a distance of 2 meter from B. Our first step is to draw the free body diagram which shows all the applied and reaction loads acting on the beam. Since the support at A is pinned, we have horizontal and vertical reactions acting at that location because pin support will prevent the horizontal and vertical displacements. At B, we have roller support which prevent only the vertical displacement and we have reactive force in the vertical direction. So this is our free body diagram.
Pinned joint at A is replaced by horizontal and vertical reactive forces, and roller support at B is replaced by the vertical reactive force.
Our next step is to calculate the reaction forces and reaction moments at all the supports. For this, we use the concept of equilibrium. To maintain the equilibrium, the algebraic sum of the forces in horizontal as well as vertical directions should be equal to 0. Similarly, the moments acting at every point on the beam should cancel each other. Here we don't have a reaction moment, we have three reaction forces. So let's start. Sum of the horizontal forces is equal to 0. Here we have only one horizontal force, that is HA. So we can say HA equal to 0. Now sum of the vertical forces equal to 0 will give us the equation minus VA minus VP plus 15 plus 10. Here I have used a sign convention as upward forces are negative and downward forces are positive.
This will give us the expression VA plus VB equal to 25. Now the third condition is the algebraic sum of the moments about any point on the beam should be 0. Let's consider the point A.
Here we have VA. Since VA is passing through A, it will not produce any moment about A. Next is 15 kilonewton. It will produce a clockwise moment about A, 15 into 2. And our next force is 10, which again produce a clockwise moment with a value of 10 into 2 plus 4, that is 6. Next force is VB. VB will produce an anti-clockwise direction which can be considered as negative with the value VB into 8. So from this we can get the value of VB as VB equal to 11.25 kilonewton. If we substitute the value of VB in this equation, we will get the value of VA. That is VA equal to 13.75 kilonewton. Now, here, since HA is 0, not shown that force, and VA is replaced as 13.75 and VP is replaced as 11.25. Our next step is to draw the shear force diagram and bending moment diagrams. For this, first we have to calculate the shear forces and bending moments at each location of the beam. Here again we use the concept of equilibrium. If we cut the beam at any location, the internal forces at that point should balance with the external loading at the left or right side of the section, so that equilibrium is maintained. This allows us to easily calculate the shear force and bending moments along the beam. What we have to do is to move the cut along the length of the beam, starting from one end, calculating the internal forces at each cuts. So let's start with shear force at A. So consider a section just after the point A. So here there is only one load, that is 13.75. So the shear at A will be 13.75. Since from A to C there is no other loads placed, shear till C will be 13.75 kilonewton. So let's mark this in the shear force diagram. See, from here it is 13.75 at A and till C it will be 13.75. Now let's consider the section at C. Just after C you can place the section. Here on the left side we have 13.75 and 15 two loads. On the right side also we have two loads. So any side you can consider. Here I am considering the left side of the section. On the left side we have an upward force which will be positive and this downward force will be negative. So the value of shear at C will be 13.75 minus 15, which is minus 1.25 kilonewton. Since from C to D there is no other load, till the point D shear will be minus 1.25 kilonewton. So let's mark these two in the shear force diagram. See, these two are already marked points and these two are the new points. Next, let's move the section to D. Just after D, you can place the section. And here this side we have three forces and here this is only one force. So it is better to consider right side of the section. And at the right we have an upward force which will give a negative shear. So shear at D will be equal to minus 11.25, and from D to B we don't have any other force, so the shear will be constant as 11.25 till the point B. Let's mark these also in the shear force diagram. See, these are the two new points we have marked. Here we have joined all the points that we have marked. A portion above the beam line will be positive and the portion below the beam line will be negative. So these are the positive shear area and this is the negative shear area. Thus we completed our shear force diagram. Let's move on to bending moment. We have a pin support here and a roller support here. So according to the support condition, moment at A equal to 0 and moment at B equal to 0. Let's mark this in the bending moment diagram. See, we have marked these 2 points. Now let's consider the section just after the point C. Here we have one load on the left side, 13.75 at a distance of 2 meter, which will produce a moment of a clockwise moment, that is left side clockwise means it is positive moment of 27.5 kilonewton, that is 13.75 into 2. Let's mark this in the bending moment diagram. Now let's move the section to the point D. On the right we have one load and the left we have two loads. So better to consider the right of the section. Here this upward load will lead to an anti-clockwise moment at the right side, that is sagging effect. So we will get a positive bending moment. So bending moment at D will be equal to 11.25 into 2, which is 22.50 kilonewton. Let's mark this also in the bending moment diagrams. This is our new point. So on joining all these points, we will get our bending moment diagram. Since it is above the beam line, this is positive.
This got our shear force diagram and bending moment diagram. Hope you understood the concept. In coming videos, beams with different types of loadings will be explained.